Throughout railroad history, engineers pushed relentlessly toward the future, convinced each breakthrough would revolutionize transportation forever. Some innovations transformed the industry exactly as promised. Others crashed spectacularly, leaving behind cautionary tales of ambition colliding with brutal reality. Today we're exploring innovations that seemed destined to define railroading's future, but instead became footnotes in the story of what went catastrophically wrong. These weren't failures of imagination. They were failures of physics, economics, and sometimes basic common sense. Isambard Kingdom Brunel believed he'd solved railroad propulsion when he proposed the atmospheric railway for Devon's south coast in 1844. The concept was elegant in its audacity. Trains wouldn't need locomotives at all. Instead, vacuum pressure would pull them through iron tubes running between the rails. A piston beneath each carriage would connect through a continuous leather valve, while stationary pumping engines positioned every 3 miles would create the vacuum differential. On paper, it promised unprecedented speeds without the weight and complexity of steam locomotives. The reality proved different in ways nobody anticipated. The entire system depended on maintaining perfect vacuum pressure across miles of track, which required the leather valve sealing the iron tube to remain absolutely airtight. But Brunel somehow overlooked what happens to leather exposed to English weather. Rain soaked through the material and rotted it thoroughly. Summer sun dried it out and cracked it beyond repair. Then came the rats. Thousands discovered the tallow grease keeping the leather supple was absolutely delicious. They ate the valve seals systematically, treating the entire railway as an endless buffet. Within months, the system leaked vacuum pressure like a sieve. Brunel spent fortunes replacing leather sections, employing crews who worked around the clock fighting decay and rodent damage. The pumping engines ran continuously, burning coal to create vacuum that escaped almost as quickly as it was generated. Maintenance costs spiraled beyond anything projected. By 1848, the South Devon Atmospheric Railway was abandoned after consuming what would equal £40 million in modern currency. The locomotives Brunel tried to eliminate returned, hauling trains across tracks that had cost a fortune to build and mere months to render obsolete. Alfred Beach secretly constructed a pneumatic subway beneath Broadway in New York in 1870. Working only after dark to avoid corrupt Boss Tweed's political interference, Beach built a tunnel where a massive fan called the Western Tornado pushed cylindrical passenger cars through, using air pressure alone. Beach completed his demonstration tunnel in just 58 nights, revealing it to amazed New Yorkers who rode in silent luxury powered by nothing but compressed air. The technology seemed miraculous until practical. Limitations emerged. The system required perfectly sealed tunnels, and any breach meant complete loss of propulsion. Fire posed extraordinary danger because passengers trapped in airtight tunnels had no escape route and limited breathable air. The single fan could only move 1 car at a time, making expansion impossibly expensive. Most damning, New York winters froze moisture in the compressed air, paralyzing mechanisms completely. Municipal authorities studied Beach's demonstration but refused to approve pneumatic transit for passenger service. London experimented with pneumatic mail tubes but banned passenger applications entirely. The technology that worked brilliantly for moving small capsules proved deadly for moving people. Before electricity revolutionized railroad lighting, passengers faced a terrifying choice between traveling in darkness or riding in what were essentially rolling bombs. Most railroads chose fire, installing coal gas lighting systems that provided adequate illumination while converting every passenger car into a potential explosion. The pinch system stored compressed coal gas in cylinders beneath cars, feeding ornate ceiling fixtures bright enough for reading. The problem was obvious to everyone, except accountants counting pennies saved on operating costs. Compressed coal gas mixed with air creates explosive atmospheres that any spark can ignite. Every derailment, every collision, carried the possibility of catastrophic explosion followed by inferno. Between 1880 and 1910, Gas-lit cars caused hundreds of fatalities in post-collision fires. The physics were brutally simple. Crash damage ruptured gas cylinders. Escaping gas mixed with air. Something sparked. People burned alive in cars that became blast furnaces within seconds. The 1887 Chatsworth disaster killed 82 people when derailed cars' gas systems ruptured and ignited, burning bodies beyond recognition. Survivors described hearing screams from people trapped behind, windows that couldn't be broken, watching helplessly as flames consumed cars they couldn't escape. State commissions began mandating electric lighting in the 1900s, but adoption was slow. Railroads argued the expense outweighed the danger, at least until lawsuits started accumulating faster than they could be settled. The innovation that brought light to night travel had transformed passenger cars into mobile crematoriums. Engineers in the 1920s believed they'd found steam salvation through pulverized coal firing. Instead of shoveling coal lumps into fireboxes, pulverize coal into fine dust and blow it in like fuel oil. Combustion would be more complete, efficiency would skyrocket, and firemen wouldn't need backs of iron. Several railroads experimented enthusiastically with systems that seemed to solve multiple problems simultaneously. Then the explosions began. Pulverized coal suspended in air doesn't just burn under the right conditions. It detonates with the force of dynamite. Coal dust explosions had killed thousands in mines for decades, but locomotive engineers somehow thought fireboxes would be different. They weren't. The problem was ignition timing and mixture control. Coal dust needs perfect air-fuel mixture and precise ignition. Too rich or too lean. And unburned dust accumulates until reaching critical concentration. Then something triggers ignition anywhere in the system. Accumulated dust explodes simultaneously, and the firebox becomes a bomb. The Pennsylvania Railroad's experimental coal dust locomotive suffered catastrophic explosion during testing at Altoona, killing crew members and destroying the test facility. The Interstate Commerce Commission investigated and recommended against the technology in 1928. By 1930, every major railroad had abandoned coal dust firing. The technology worked beautifully in controlled power plants with computer monitoring and safety systems. It proved impossibly dangerous in the violent, unpredictable world of locomotives where conditions changed constantly and automation didn't exist. The Fireless locomotive seemed perfect for industries where smoke and sparks posed unacceptable risks. Chemical plants, textile mills, and ammunition factories needed switching power, but couldn't tolerate open flames. These locomotives carried no firebox whatsoever. An oversized boiler was charged with superheated water and steam from stationary sources, and pressure differential powered the engine until stored energy depleted. The concept worked within severe limitations that prevented wider adoption. A fully charged Fireless locomotive could operate roughly 2 to 4 hours before needing recharge, limiting range to perhaps 5 miles under load. Efficiency dropped catastrophically as boiler pressure declined, meaning the locomotive was strongest when freshly charged and nearly useless before recharging. Winter operations were particularly problematic as heat loss accelerated dramatically. Crews reported locomotives losing half their operating time in cold weather simply from thermal losses. Mainline commissions banned Fireless locomotives from interchange service because they couldn't maintain schedules or operate beyond charging stations. The Federal Railroad Administration never certified any Fireless design for common carrier operation. They remained confined to industrial switching yards, representing an engineering compromise that solved specific problems while creating others too significant for wider adoption. Today, surviving examples sit in museums as curiosities, proof that some innovations succeed only in narrow niches. Thomas Edison predicted battery-powered locomotives would revolutionize railroads. He spent years developing storage batteries specifically for railroad traction, convinced silent electric power would replace smoky steam. Other inventors followed, building experimental battery locomotives that promised clean, efficient operation. They were all decades too early. The problem was energy density that made the concept impractical with available technology. Steam locomotives convert chemical energy from coal with brutal simplicity. Battery locomotives must carry the weight of their energy storage, which meant lead-acid cells weighing tons per hour of operation. The numbers never worked. A typical steam locomotive could operate all day on coal carried in its tender. An equivalent battery locomotive needed cells weighing more than the locomotive itself to achieve even 4 hours of operation. The weight crushed the very efficiency gains batteries promised. Several railroads tested battery locomotives between 1900 and 1920. All discovered the same fundamental limitation. Range was measured in miles, not hundreds of miles. Recharging took hours using primitive electrical infrastructure. Battery life was measured in months before expensive replacement became necessary. The economics collapsed under examination. Edison's batteries worked beautifully for lighter applications, but the power demands of railroad traction exceeded what electrochemistry could deliver economically. Battery locomotives disappeared, waiting for lithium-ion technology that wouldn't arrive for another century. When Pennsylvania Railroad commissioned Baldwin to build experimental duplex locomotives in the late 1930s, they promised machines combining Pacific speed with northern pulling power. Baldwin delivered the S1 in 1940, an absolute monster stretching 140 feet from coupler to coupler and weighing over 1 million pounds with tender. It was possibly the largest passenger steam locomotive ever built and far too big to be useful anywhere except drawing boards and publicity photographs. The S1's 6-foot 4-inch wheel arrangement looked revolutionary. Raymond Loewy's streamlining made it appear to be traveling at speed, even standing still. But beneath that gorgeous shell lurked fundamental flaws that made the locomotive nearly useless. It couldn't navigate most of Pennsylvania Railroad's network. Turntables couldn't handle its length. Curves threatened derailment on any but the straightest main lines. PRR restricted it to just 283 miles between Chicago and Crestline, a fraction of the system it was meant to revolutionize. Wheel slip plagued every run. With driving wheels divided between two sets under a rigid frame, achieving balanced adhesion proved impossible. At high speeds, the locomotive surged unpredictably as one driver set slipped and caught repeatedly. Engineers described fighting it like riding a mechanical bull, constantly adjusting throttle and brake to prevent violent slipping that could strip gears and damage running gear. The S1 ran just 6 years before scrapping in 1949, teaching Baldwin and PRR exactly nothing about why duplex designs kept failing so spectacularly. The Pennsylvania Railroad Q1 emerged from Altoona Works in 1942 as the next duplex experiment, this time for heavy freight service. Streamlined by Raymond Loewy, this imposing 4644 looked like the future of freight power. Instead, it proved some fundamental engineering mistakes refused to stay buried, no matter how pretty the shell. The designers mounted rear cylinders backward-facing toward the firebox, which seemed clever on paper. It kept the locomotive shorter and balanced weight better. In reality, it created mechanical nightmares nobody anticipated. Firebox heat baked those rear cylinders constantly. Ash infiltrated every seal and bearing surface. Steam pipes stretched so far that pressure dropped dramatically before reaching pistons, robbing the locomotive of power it desperately needed. Making matters worse, PRR gave the Q1 passenger-sized 77-inch driving wheels on a freight locomotive, like putting racing tires on a dump truck. It struggled with heavy starts and couldn't develop proper tractive effort at low speeds where freight locomotives live. During its brief career, the Q1 accumulated just 165,000 service miles. Ordinary freight locomotives routinely passed 1 million. PRR learned enough from the Q1's failure to redesign everything for the Q2, building 26 units between 1944 and 1946. The Q2 fixed backward cylinder problems by mounting all 4 cylinders ahead of the wheels they drove. The firebox grew large enough for sustained hauling. An automatic wheel slip control system attempted to prevent violent slipping. But they still consumed water, like the ocean was running dry, and maintenance remained a nightmare. All were scrapped by 1953, replaced by diesel locomotives that actually worked. The Baltimore and Ohio's George H. Emerson emerged in 1937 as America's first true duplex locomotive. Built at B&O's Mount Clair shops, this experimental 4444 carried the name of the railroad's chief of motive power. Perhaps they should have waited to see if it actually worked before permanently attaching his name. Rear cylinders ran hot and wore out far too quickly. The dual throttle system required engineers to manually balance power between driver sets. Maintenance crews found critical components buried in hopelessly inaccessible locations. The B&O tested the Emerson for 6 years without ordering additional units. By 1943, it was quietly retired. In 1944, Pennsylvania Railroad unveiled the S2 steam turbine that made no chuffing sound, just continuous whooshing as 6,900 horsepower drove wheels through a massive gearbox. It was supposed to combine steam's fuel economy with turbine smoothness. It achieved neither. The S2 represented the ultimate effort to make coal-fired steam competitive with diesel at a time when the writing was already on the wall. Built by Baldwin and Westinghouse, the S2 used a direct-drive turbine geared to driving axles. The gearbox transmitted power with 97% mechanical efficiency at high speeds, which sounds impressive until you understand turbines' fatal characteristic. They're incredibly inefficient at low speeds. Above 40 miles per hour, the S2 performed magnificently, maintaining 100 miles per hour while pulling heavy trains with fuel economy approaching diesel levels. Below 30 miles per hour, it became a fuel-guzzling monster. Starting from rest, the boiler couldn't keep up with steam demand. Pressure plummeted from 310 psi to below 185 within minutes. The firebox ran so hot at low speeds that stay bolts cracked repeatedly, requiring constant repairs. Real-world railroading involves constant acceleration, deceleration, stops, and starts. Trains accelerate from stations, slow for curves, stop for signals, and crawl through yards. The S2 excelled at exactly one thing, sustained high-speed running, and failed at everything else. By 1949, severe turbine damage ended the experiment. The locomotive was scrapped in 1952, having logged just 103,000 miles before proving turbines belong in power plants running at constant speed, not on rails where conditions change every minute. Norfolk and Western's John Henry stretched 161 feet from coupler to coupler, making it the longest steam locomotive ever constructed. The boiler operated at 600 pounds per square inch, nearly double conventional pressure. Coal dust infiltrated the electrical equipment constantly, destroying traction motors and generators. The complex controls confused even experienced engineers. Performance ran 15% below the conventional Class A locomotives it was supposed to replace. Norfolk and Western scrapped it in 1958. 3 massive steam turbine electric locomotives emerged from Baldwin Westinghouse between 1947 and 1948, designated M1 class. Coal dust proved to be their nemesis. Fine particles infiltrated the traction motors constantly. Crews reported motors burning out on nearly every run. The boiler controls proved temperamental. The turbine electric drive system added complexity that steam crews couldn't maintain, and electric crews it didn't understand. Within a few years, all 3 sat dead in storage. They were scrapped by 1953. Baldwin built the first triplex for the Erie Railroad in 1914, naming it the Matt H. Shea after a beloved company engineer. The concept seemed logical. Put 3 complete engine sets on one locomotive frame, achieve unprecedented tractive effort, and eliminate the need for multiple helper engines on steep grades. The reality proved that some problems cannot be solved by simply adding more cylinders. The Matt H. Shea generated 160,000 pounds of tractive effort, more than any steam locomotive before or since. But that power came with crippling limitations. The single boiler couldn't generate steam fast enough to feed 3 sets of cylinders at anything above a crawl. Crews discovered the triplex could start almost any train, but couldn't accelerate it. Speed topped out around 10 miles per hour before steam pressure dropped to useless levels. Making matters worse, one engine set was mounted beneath the tender. As coal and water were consumed, weight decreased, and that rear engine lost adhesion. Starting fully loaded, the tender provided excellent traction. Halfway up a grade with supplies depleted, those rear wheels spun uselessly while the front engine sets strained to compensate. The Matt H. Shea spent more time in shops than on the railroad. Erie eventually cut it apart and rebuilt it as 2 separate conventional locomotives. Even the railroad's official designation acknowledged the experimental nature. The designation stood for failure, barely disguised. Between 1914 and 1916, American Locomotive Company built 3 massive triplex locomotives for the Erie Railroad's mountain grades. These 28882 behemoths featured the same 3-engine concept as the later Virginia machines, but with an even more complex arrangement. The tender itself was powered, with 1 set of driving wheels beneath the coal and water supply. On paper, the Erie triplex looked revolutionary. 3 connected engine units would provide 160,000 pounds of tractive effort, enough to move mountains. Erie needed exactly that kind of power for the steep grades through New York's southern tier. Reality was less cooperative. Like all triplex designs, the single boiler could not keep pace with the steam demands of 3 engine sets at anything above a crawl. Crews nicknamed them yard rippers because they excelled at pulling long trains out of terminals, but could not maintain speed on the main line. The powered tender created additional problems as weight shifted unpredictably during operation. The engine units fought each other rather than working together, with some wheels slipping while others grabbed, creating lurching motion that damaged couplings and terrified crews. All 3 Erie triplexes were eventually rebuilt into more conventional configurations. The triplex concept died on those grades, a bold idea that simply could not overcome the physics of steam generation. Pennsylvania Railroad's T1 Duplex represented everything learned from previous duplex failures, which apparently wasn't nearly enough. 52 of these streamlined 4444 locomotives were built between 1942 and 1946, designed by Raymond Loewy to be the fastest passenger power in America. They achieved that goal, reportedly touching 140 miles per hour on test runs. They also concealed a fatal flaw that made them nearly uncontrollable in regular service. The divided drive arrangement placed 2 sets of driving wheels on a rigid frame, each powered by its own cylinders. This made the T1 extraordinarily prone to wheel slip, violent wheel slip that occurred without warning at any speed. Engineers reported front drivers spinning wildly while rear drivers gripped normally, sending shudders through the locomotive that could be felt in the passenger cars. The poppet valves chosen for quick steam admission made problems worse by delivering power in sudden bursts instead of smoothly. Operating departments found them unreliable and difficult to maintain. Wheel slip damaged valve gear, which caused more slip in a vicious cycle. By 1948, Pennsylvania Railroad had begun replacing their revolutionary T1s with diesel locomotives. Every single T1 was scrapped within a few years. None were preserved. The entire fleet was erased from existence, railroad management apparently ashamed of having built so many examples of such a spectacular failure. Atlantic Coastline's R1 arrived in 1938 as Baldwin's grand proof that duplex power could actually work. It didn't. With 2 sets of driving wheels under a rigid frame, getting equal adhesion proved impossible. Engineers spent more time fighting wheel slip than running trains. The backward-facing rear cylinders ran hot constantly, and accumulated grit. ACL tested it barely 3 years before quietly returning it to Baldwin. The manufacturer never spoke publicly about this locomotive again. Despite this humiliating failure, Baldwin convinced Pennsylvania Railroad to try duplex power anyway. Between 1877 and 1887, 38% of all rail worker accidents involved coupling operations. During the 8 years before federal regulation, workers killed and injured equaled the total American railroad workforce in a single year. The Safety Appliance Act of 1893 mandated automatic couplers, specifically the Janney knuckle design. Coupling accidents dropped from 11,000 in 1892 to 2,000 by 1902. These innovations reveal how railroads balanced progress against practicality, often choosing poorly. Some failed because physics wouldn't cooperate. Others failed because economics made operation impossible. A few failed because they arrived after the technology they were meant to save had already been rendered obsolete. What unites them all is the gap between promise and performance, between engineering drawings and operational reality. The Duplex locomotives promised to combine speed with power through divided drive. They delivered wheel slip and maintenance nightmares. High-pressure boilers promised efficiency through thermodynamics. They delivered complexity and sometimes death. Turbines promised smooth power and fuel economy. They delivered efficiency only at sustained high speeds railroads couldn't maintain. Atmospheric and pneumatic systems promised to eliminate locomotives entirely. They delivered rats, weather damage, and operational impossibility. Each failure taught lessons the industry sometimes learned and sometimes ignored. Duplex locomotives failed repeatedly across multiple railroads before the concept was finally abandoned. High-pressure steam killed people before being recognized as impractical with available metallurgy. Pulverized coal exploded before engineers accepted that mines and locomotives faced different safety challenges. Some innovations failed once and disappeared. Others required multiple disasters before being consigned to history. The broader pattern reveals how desperation drives bad decisions. The 1940s duplex and turbine experiments weren't stupid engineering. They were desperate attempts to save steam from diesel domination. Engineers knew internal combustion was winning. They gambled that one more breakthrough, one more radical design might reverse the tide. Every failure pushed steam closer to extinction, while diesel locomotives proved their superiority through reliable, economical operation that required no breakthroughs, just steady refinement of proven technology. The innovations that succeeded were those that solved real problems without creating worse ones. Automatic couplers eliminated coupling deaths while actually working reliably. Electric lighting provided illumination without explosion risk. Enclosed vestibules protected passengers without adding prohibitive complexity. These innovations succeeded because they made railroading safer and more efficient simultaneously. The failed innovations promised efficiency or power while delivering danger, complexity, or operational impossibility. Looking back across railroad history, the failed innovations serve as reminders that engineering brilliance means nothing without practical application. A locomotive that performs magnificently under ideal conditions but fails under real-world operation is worthless. A system that promises theoretical efficiency but requires maintenance beyond available expertise cannot succeed. An innovation that arrives after the technology it's meant to save has already been condemned is doomed regardless of technical merit. These 20 innovations didn't fail because engineers were incompetent. They failed because railroad operation is brutally unforgiving of theoretical elegance that doesn't translate to practical reliability. The gap between drawing boards and mainline operation proved too wide for atmospheric railways, pneumatic subways, pulverized coal firing, duplex locomotives, turbine drives, high-pressure boilers, and dozens of other promising concepts. Each taught expensive lessons about why proven, reliable technology beats innovative, complicated alternatives almost every time. The railroads that survived and prospered were those that recognized when innovation had become liability. Diesel didn't win through technological superiority in every metric. It won through reliable simplicity that reduced operating costs and increased availability. Steam's last innovations were often its most complex, desperate attempts to match diesel efficiency that only proved diesel's fundamental advantages. Don't forget to subscribe so you don't miss future explorations of railroad history where ambition met reality. Here's another video I've specially selected for you. See you next time.